In this lecture, we will learn section 12.5 equations of lines and planes. Suppose we have equation of a parabola y equal to x square. So y equal to x square is the Cartesian equation of the parabola. Sometimes it also called rectangular equation. Now suppose we want to convert this equation to parametric equation. So let x equals to t, and where t is a parameter, and if you plug x equals to t here, then y becomes t square. So x equals to t and y equal to t square is the parametric equation of this graph. Now the vector function r of t would be x of t comma y of t, where x of t is t and y of t is t square. So this is the vector function of this graph. So you can think that a vector function as a system of parametric equation with parameter t. Now in this example, we have the vector function r of t equals to t comma 4 minus t. So x equals to t and y equal to 4 minus t, and we wanna sketch it graph. Now if t equal to 0, x becomes 0, y becomes 4. If t equals to 1, x becomes 1, y becomes 3. If t equals to 2, x becomes 2, y also 2. Similarly, you will get other 2 points. Now on the xy plane, if you plot those points and add them together, then you will get a straight line. That means this straight line is the graph of this vector function. Even you can sketch this graph by converting it to Cartesian equation. So if you plug t equals to x here, then it becomes y equal to 4 minus x. It will represent the same straight line. In 3 dimension, we have a vector function r of t equals to t 0 1, where t is any real number. We need to sketch its graph. So x equals to t, y equal to 0, and z equals to 1. So when t equals to 0, then x becomes 0, y is 0, z is 1. So we'll get this point. When t equals to 1, we get 1, 0, 1. Similarly, when t equals to 2, we get 2, 0, 1. Now if you plot those points, so 0, 0, 1, so it will go 1 unit to the z-axis, 1 unit to the z-axis. This point will go 1 unit to the x-axis, 1 unit to the x-axis. There is no unit along y-axis, but 1 unit along z-axis. So it will go here. Now similarly, it will go 2 units along x-axis and 1 unit along z-axis. So it's here. Now if you add those points, you will get a straight line. Now we need to find equation of a straight line. In 2 dimension, we know that if a straight line passes through the point P0 equals to x0, y0 and have a slope m, then its equation is y minus y0 equals to m times x minus x0, where P0 is the fixed point and this P equals to xy is a general point on the straight line and m is the slope. Now in 3 dimension, if P0 equals to x0, y0, z0 like this one is a fixed point, so P0 is the fixed point and P is the general point on the straight line. This P can be anywhere on the line. And suppose we have a direction vector v equals to abc. This direction vector is like slope. Then its equation would be this one. Although it looks complicated, but we will derive it. We know if a straight line passes through the point x0, y0 and x1, y1, then slope m equals to y1 minus y0 divided by x1 minus x0. Rise over run. That means del y over del x. Similarly, if a straight line passes through the point x0, y0, z0, x1, y1, z1, then its direction vector v would be, so direction vector v would be x1 minus x0, y1 minus y0, z1 minus z0. So this is del x, del y, del z. And we normally define direction vector as a, b, c. So this direction vector is always parallel to P0P. So P0P is parallel to V. Since they are parallel, so one would be scalar multiple of another one. So P0P can be written as T times V, where T is a non-zero number. And P0P is x minus x0, comma, y minus y0, comma, z minus z0. And TV would be TA, comma, TB, comma, TC. Now, the first component x minus x0 equals to TA. So, x minus x0 equals to TA, and x would be x0 plus AT. Similarly, second component y minus y0 equals to TB, y minus y0 equals to TB. So, y would be y0 plus BT. And similarly, we will get this. So, equation of the line is x0 plus AT, y0 plus BT, z0 plus CT. This one. Now, in this example, we need to find equation of the straight line that passes through these 2 points. Now, suppose P0 is 1, 2, 1 and P1 is 3, 0, negative 1. The direction vector V would be x1 minus x0, that means 3 minus 1, which is 2, y1 minus y0, that means 0 minus 2, which is negative 2, and similarly we will get negative 2. Now, if we consider the fixed point P0 as x0, y0, z0, which is 1 to 1. Now, x would be x0 plus AT, x0 plus AT. So x0 is 1 and a is 2, so 1 plus 2t, and y is y0 plus bt, so y0 is 2 and b is negative 2, so 2 minus 2t, and similarly we will get this one. So the vector function is r of t equals to 1 plus 2t, 2 minus 2t, 1 minus 2t. So this is equation of the straight line. Now here I consider P0 as 1 to 1. I consider this is as the fixed point. Now if you consider this one as the fixed point, then you will get this function. Now although this one and that one looks little different, but they represent the same straight line. It is just in different forms. Now equation of a plane. Suppose this is a plane and on the plane we have 2 points, P0 equals to x0, y0, z0 and P equals to x, y, z. This P0 is a fixed point on the plane. So this P0 is a fixed point and this P is a general point on the plane. So it can be anywhere on the plane. This P can be anywhere on the plane. And suppose n is perpendicular at P. So n is a perpendicular vector at P. Now P0P is perpendicular to n. So this n is orthogonal or perpendicular to the plane. So P0P is perpendicular to n, and from the dot product we learned that if two vectors are perpendicular, then the dot product is 0. So P0P dot n is 0 and P0P is x minus x0, y minus y0, z minus z0, and n is ABC equals to 0. Now from the dot product we learned that the dot product of two vector is a times x minus x0 plus b times y minus y0 plus c times z minus z0, which equals to 0. Now, if you simplify, it becomes ax plus by plus cz equals to ax0 plus by0 plus cz0. Now, if we think, or if we let this one equals to d, then equation of the plane becomes ax plus by plus cz equals to d. In this example, we need to find equation of the plane that contains these 3 points. So suppose P is here, Q is here, and R is there. Now if we add PQ, and suppose this vector is U, so U equals to PQ, and U would be Q minus P. So 1 minus 0 is 1, 0 minus 1 is negative 1, 1 minus 1 is 0. And suppose V equals to PR, V equals to PR, so V would be R minus P, that means 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is minus 1. Now, from the lecture of cross product, we learned that if we take cross product of two vectors u and v, then u cross v would be perpendicular to both u and v. So if we take cross product of u and v, then it would be perpendicular to the plane. So this n is perpendicular to the plane. So n is, we got 1 1 1. Now consider the fixed point P0 as 0 1 1. So x0 y0 z0 is 0 1 1 and n is 1 1 1 1 1 1. This is A, B, C. Now from the equation of the plane, we know that ax plus by plus cz equals to d. So if you plug the value of a, b and c here, you will get x plus y plus z, and d equals to, we know, ax0 plus by0 plus c z0. So plug the value of a, b, c, x0, y0, z0 here, and after simplifying we will get d equals to 2. So the equation of the plane that contains these 3 points is x plus y plus z equals to 2. Now in this problem, I consider P0 as 0 1 1. Now if you consider any other point, suppose Q, here we consider Q, then we will get the same equation, x plus y plus z equals to 2, the same equation. Even if you consider R as P0, then you will also get the same equation. So it doesn't matter which point you will choose. Now in next problem, we also need to find equation of a plane that contains these 3 points. So same way, so U equals to suppose PQ and V equals to PR. So U becomes, if you subtract Q minus P, it becomes 1 1 1, and V becomes R minus Q, sorry, R minus P. This is 2 2 2. Now if you take cross product of these two vectors, this becomes 0. So it's dead end. So there is an infinite number of planes that contains these 3 points. Now what we can do, let's choose the plane that also contain 0 0 0. So if we consider O as 0 0 0, now suppose OP is U and OR is V, then U would be this one and V would be that one, and N would be 2 negative 1 negative 1 if you follow the same procedure. Now after simplifying, we will get the equation of the plane as this one, twice x minus y minus z equals to 0. If you plug x, y, z equal to 0, 0, 0, then it satisfies the plane. If you plug x equals to 1, y equals to 2 and z equal to 0, so x equals to 1, so 2 times 1 is 2 minus y equals to 2 is also 2 and z equal to 0, so both sides become 0. So all of the points satisfies this equation. That means all of this point lies on this plane. That's for today's class. We will discuss more on next class. Thanks.